Just not Jose.
That's useful. Nobody knows who you are.
Are you close to submitting? Yes. Are you excited? Yeah. Because you need to submit and then start packing. You have 1 week to pack.
All right.
Yeah,
Welcome,
maybe
everyone.
in 1 week.
Hello. Yep. Hi, guys. Thank you for coming. This is the last event of the SFP UQ student chapter, and many of you have been coming to many of the events this year, so thank you very much. And I don't know if anyone from a few people from the school are here, so thank you to the School of Civil Engineering who have supported us this year, and also, of course, UQ Fire. Well, I'm pretty sure you know who's gonna give the talk. I don't need to introduce him, but he's Professor Torero. He comes from University College London, and he's gonna give us this talk about guided by the light of knowledge continuity. And I asked him to make it a little bit more informal than the one that he already gave at University of Edinburgh, but yeah, it's up to him, so enjoy, guys, and thank you for coming.
Well, thank you very much. It's always a real pleasure to be here and seeing some new faces, but also seeing some old faces, particularly Peter. And it's great to be here. And so Jaime asked me to repeat a talk that I gave in Edinburgh a few months ago, and it was a talk that was directed for students working in the area of fire safety, which tried to give people a little bit of a context of basically why we are where we are. And when I say that, I say it with a little bit of sarcasm, I guess, because we are in a very deep hole right now. So as a discipline, fire safety is being questioned left and right. We've gone through a series of very complex failures, and those very complex failures have remained unexplained, and to the point that we keep making the same mistakes without really truly understanding why are we making those mistakes. Now, when that happens, people try to find mechanisms, by which they justify intervening. So if you have a group of people that cannot fix their own problems, there's going to be always somebody that thinks and knows better. And so right now, it is actually quite fascinating what is happening around the world. And Australia is a perfect example of that, but the United Kingdom and many other places are going through the same process. We have structural engineers, civil engineers telling the fire engineers what to do because they believe or recognize that they truly don't have the capacity to deal with the problem by themselves. We have lawyers now involved left and right telling us all what to do. And a perfect example was Sir Martin Moore-Big or Bronwyn Weir here in Australia, where effectively they can write reports about what we should be doing and what we should not be doing from a legal perspective. In the case of the La Crosse fire, there was a very damning report by the judge who effectively attributed a very significant part of the blame to the fire engineer. And under a principle that I thought was quite interesting, which is just simply balancing the credibility of experts. So the lawyer or the judge sits from the podium and says, this is not my field, I don't understand anything they're talking about, but this group of experts sound much more credible than this group of experts. And as such, I'm going to adjudicate against the fire engineer who effectively has to take a big brunt of the losses. So as you can see, we've got to the point that even the architects now think they know better. And the Royal Institute of British Architects now is creating guidelines to educate people on fire engineering. And the moment where the architects believe that they know better than the engineers, that's the moment where we really know we're in trouble. It's clear that you cannot sink lower than that. Okay, so we have to be very conscious of that, and this is a real serious issue that we need to address. Now, fire engineers have made many mistakes in the way they're answering this particular type of questions, and one of the mistakes that is very often made by fire engineers And I was at this meeting in Brussels a few days ago, and a very prominent professor, who calls himself Professor of Fire Science, made a big statement saying, oh, well, you know, we are a very young discipline. You know, and as such, you know, like children, we cannot be blamed, okay? Nevertheless, you have to recognize that if you attribute yourself, you know, the nature of a child, that effectively enables paternal guidance. And this brings us back to the position where the architects are telling us what we should be doing. So, and I think this kind of myths, you know, of how new our discipline is and so forth, are myths that effectively we need to address, because that is really not at the core of our problem. And we need to recognize actually if we are such a new discipline or not. And I'm going to try to make the case that we actually are not. We are probably one of the oldest and most well-structured engineering disciplines. And therefore, you know, we should not be arguing the fact that we are so new that, you know, we require paternal guidance, because we don't, okay? Now, on the other hand, we are addressing a very complicated problem. And the moment that you are addressing a very complicated problem, you know, all of a sudden you fall into a space that is effectively the space of professional competency. You know, if you have a very simple problem, a problem that is of small importance, then effectively you can allow people to do whatever they want. But if you're addressing an incredibly complicated problem, then all of a sudden you have to start regulating the practitioners, because these people have to respond to a problem that is a fundamental problem that affects society, that is of such level of complexity, that needs to be addressed only by a selected group of individuals that are sufficiently competent to be deemed as acceptable to operate in that space. So it is not that we are a young discipline. You know, it is not that we are a new discipline that doesn't have methods and so forth. It is that we are a discipline that addresses an incredibly complex problem of huge societal impact. And as such, it belongs to the realm of professional competency. Okay, just like doctors do, or lawyers do, or structural engineers do, this is a space where effectively we should be claiming professional competency as a monopoly of a group of people that really know what they're doing, because mistakes end up costing us a lot. So situations like the Grenfell Tower fire are a series of mistakes of a nature such that eventually ended up costing the lives of 72 people. So effectively, that is the essence of what I'm talking about. So that I don't put photographs, you know, for no reason. That photograph is of Battersea power plant in London. And in a way, the reason why it's there is to show complexity. Look at all those cranes operating into a building of a magnitude, size, and complexity that is absolutely extraordinary. You know, and therefore, the people that are involved in the analysis and design of that building should be people that are selected among the few that are capable of delivering such a project. So if you look at the list of credits for the Battersea, you know, redevelopment, the master plan was done by Raphael Vignoli, a New York architect, extremely famous, did a lot of really ugly buildings, but nevertheless, very, very famous. His buildings are really unique, okay? Every component was assigned to one of the star architects. So you have a sector by Richard Royers, a sector by Norman Foster. You know, they're all sectors, and they're all assigned to extraordinary architects. So if you look at the list of structural engineers, you know, you have Irving Cantor, you have Thornton Tomasetti, you know, you have every star structural engineer involved in this particular project. And the list of credits are all there. Even when you look at the building services, you will have people whose names are there. And then you wonder, who were the fire engineers? They're nowhere to be seen.
Torero.
Oh, you wish. They would never want me there, because I will slow their project with way too many questions. But the reality is that, you know, in principle, you would say that you should be looking, for somebody that actually has a name, no? That people can recognize as being consistent with the level of complexity. But the reality is that that is not there. So let me then make my case, okay? And explain little by little, why, I'm saying what I'm saying and why these myths are actually not real. Okay. So the basis of what I'm saying is that innovation in this type of spaces is not fortuitous. And it's not about just purely your imagination, and it's not about having the great idea, but it is the product of cumulative knowledge that leads to the competency, and only competency enables innovation. Now, what do I mean, by this? So if you watch Mark Zuckerberg's Facebook movie, okay? When was this moment of genius? The man just broke with his girlfriend, he's completely upset, he gets completely drunk in front of the computer, he has an incredibly bright idea, and that bright idea all of a sudden, the next morning, is materialized into Facebook, and now the guy is a multi-billionaire. Can that happen in the space of infrastructure? Is that possible? You see, the world of infrastructure is full of trivial solutions. What do I call trivial solutions? I come to the first year class, and I give them an incredibly complex structural problem, and I say, well, brainstorm, and give me a solution to this incredibly complex, problem. So 5 or 6 first years are going to sit there, they're going to brainstorm. They don't have to be drunk, they don't have to be broken up with their girlfriends, but they can brainstorm, okay? And they can discuss it endlessly. What they're going to tell me at the end of the day is a trivial solution, okay? Because whatever thought process that they put in there, whatever imagination they put in there, is devoid of knowledge. They don't have the knowledge that enables them to understand that people have already built an entire body of knowledge that has tried and failed many solutions. All these trivial solutions have been tried and failed until you get to the point where you know enough that you know where you can play so that you can come up with an innovation. Of course, you have to have the great idea, but without the knowledge, the great idea is most likely going to be a trivial solution. So if we don't build on the knowledge of others, then effectively we can never achieve that innovation. Now, this is very important because this is the reason why many times disciplines like civil engineering, heat transfer, fluid mechanics, where there's an enormous body of knowledge, are perceived as being very non-innovative. People always argue that we move at the pace of an elephant very slowly, but the reason is that that is just natural because you have to learn a lot before you get there. And once you have that knowledge and you build it in, then you have the capacity to play. There's a famous interview with a pianist called Arthur Rubinstein, where he is giving one of those master classes to students. And basically he says that before you can interpret, okay, your fingers have to be agile enough and your skill has to be completely developed. Only then you will free yourself from the constraints of your physical capabilities and your technique and be able to start interpreting music. Without all that background knowledge, you will never be able to sit down and present a unique and extraordinary version of a piano sonata. Okay? So the problem is that we have learned to believe that innovation is innovation that happens like that. And how have we learned to believe that? Because in the last 15 or 20 years, the space of great successes has been space where people were actually developing things from scratch. The computer science is something that didn't exist 100 years ago. So effectively then, all the knowledge was fresh and brand new, and we were doing the first steps into the development of original ideas. Okay? Now, the problem is that in civil engineering, we've been doing this for a very, very long period of time. In fire engineering, we've been doing this for a very long period of time. So we need that cumulative knowledge to be able to get here. Okay? And without that cumulative knowledge, then effectively we cannot get to the element of innovation. So effectively, if somebody is going to be designing the Burj Khalifa, a lot of things have to be learned and done before you're capable of providing the unique solution that enabled the tallest building in the world. Okay? So where does that start? And how that knowledge was actually built is something that is really important, and it requires a deep understanding to know on which shoulders are we standing. Because that's what enables us to get to the point where we're capable of providing something new and different. So it all starts there. So effectively, if you didn't have ranking, so William Rankin developed the whole concept of how you can actually create forces in frames. So in this particular type of building, you're going to have the same type of mechanics or statics that Rankin developed, more than a century ago. And from that information, then you have people like Telford, for example, that recognized that all that information needed to be structured around the concept of a profession. So for example, the first organization in the United Kingdom that formalized engineering as a discipline and introduced concepts like the ones that Rankin put in place was founded by Thomas Telford, who effectively was, and people don't know that, people know Telford for all his bridges. But actually Telford, his first extraordinary jobs were actually tall buildings. So some of the first tallish buildings in London that were 6-7 stories were designed by Telford. And basically it was a new application of concepts like the ones that Rankin developed towards the development of taller buildings. So they start optimizing load redistribution and a number of different things in such a way that they could actually construct slightly taller buildings. Perfect example is King's College in London, which is a fairly tallish building because it's actually very narrow and kind of tall. And that was designed by Telford. So effectively, you start seeing how that starts being built. And then it starts being structured around the concept of a profession. Now, once you get that, then you have things like Eiffel. So if you think of Gustav Eiffel, when it comes to structures, we always think of the Eiffel Tower, okay? But from the perspective of innovation, so the Eiffel Tower is a tall structure. At the time, it was the tallest structure in the world. But from the perspective of innovation, Eiffel's great innovation was actually quality control. So he imported the components, the materials from different places to make sure that the tolerances were right, that the quality of the material was right, and in a way it was an optimization of quality control that became absolutely necessary when you start building structures that are taller and taller and taller and taller. So if you don't manage the quality control of the components of the system, you start propagating your mistakes, and the taller the building is, the more dangerous that becomes. So in what concerns tall buildings, Eiffel's contribution was one of quality control. Now, Eiffel had a classmate, classmate of Eiffel was this guy called William Le Baron Jennings, and so they studied together at the École Centrale in Paris, and he brought a lot of the same knowledge that Eiffel used in the Eiffel Tower, he brought it to the United States. And this is what is considered the first North American high-rise. So this particular building, the home insurance building in the city of Chicago, is considered to be the first North American high-rise. Now, what is the innovation in that particular building? Now, the same skills that Eiffel had put into the Eiffel Tower now were used in a building where actually people were going to occupy it. Okay, and that brings all sorts of other issues, because effectively you don't have, for example, the prerogative of being able to taper the building the way he tapered it here, so that you actually distribute the weight, to the bottom, and that addresses a whole bunch of geotechnical issues at the level of the foundations. Okay, well here you have a building where you have to optimize the use of the floor plan, which effectively doesn't allow you to taper the building, which minimizes the surface area, so it enhances the relevance of having proper foundations. Okay? So all of a sudden you can see how these innovations are all creeping, and they're all beginning to form the knowledge base that enables us to build taller and taller and taller buildings. Now, the next level is about 40 years later, and this will be William Randolph Squire, and he designed the Chrysler Building. So the Chrysler Building introduced the concept of a rigid core. Now, why the rigid core was necessary? Because they were talking about now buildings that were tall enough that wind loads became an issue. And the moment wind loads became an issue, then you have to find innovative ways by which you actually gain the right stiffness, for the structure. And then the rigid core became the innovation, and that was enabled by the potential use of steel. So again, now we're moving into new materials, we're learning how to use new materials, and we're learning how to put them in certain forms that allow us to build taller and taller and taller and taller buildings. Now, he was also famous for a very interesting phrase. So this is an Art Deco building. So this Art Deco building, admired by how beautiful it is, the way he described Art Deco was, he said, Art Deco is a blanket of beauty on top of engineering prowess. Because effectively this building is purely engineering. And then they, sort of put a nice blanket that looked really beautiful on top of it, and resulted in this very famous Chrysler building. So now we've got to a very tall building, okay? And you can see that little by little, and I could have put 25 other innovators in there, but you can see how the knowledge is building. No? And it's building to the point where you can actually start achieving buildings that now begin to look like the Burj Khalifa. Now, the moment that you get there, then you start looking into other individuals. So here it was steel, but then the use of concrete technology in very innovative ways can be attributed to Ove Arab. So Ove Arab, this particular building here is called the Penguin Pool at the London Zoo. And you can see the very slim concrete elements that were used for that. And Arab was very, very famous for being able to use concrete in a very unique way. Now, this particular building, the Burj Khalifa, is very high-strength concrete, very unusual type of material. So it required people like Arab that enabled the use of these complex concrete materials into very innovative structural shapes. Now, finally, you get to Fazlur Khan, and when you get extremely tall, obviously wind becomes the big issue. And the way in which wind creates a load on the building depends very much on its shape. So if you actually start playing with the shape of the building, you can change the pressure distribution, and as you change the pressure distribution, you can achieve better and better and better optimized buildings. Now, that is mostly due to Fazlur Khan, and buildings like the John Hancock is a perfect example of beautiful load redistribution systems that effectively enable a very efficient structure that can cope with wind loads in a very effective way. Okay? So, a disciple of Fazlur Khan, same company, Skidmore, Owens and Merrill, eventually is Bill Baker, and Bill Baker is the designer of the Burj Khalifa. One of the particularities of the Burj Khalifa is that when it was originally conceived, the developers, a company called Emaar, which belongs to the royal family of the Emirates, they wanted the tallest building in the world. And they had commissioned the tallest building in the world, but that was in the year 1998, okay? So they started designing the building, and then 2001 happened, there was the World Trade Center collapse, and there was a loss of confidence in tall buildings, so they decided to shrink the project, and they decided to more or less settle for about 500-meter building. So they didn't want a building that was that tall. So what ended up happening was, when construction started and the foundations were put in place, they were planning on having a 500-meter building. By 2004, confidence had built up, and then Emaar wanted the tallest building in the world again, and they start changing the brief. So when I heard Bill Baker give this talk at the Institution of Structural Engineers, where he was explaining what the whole sequence of events was, and how at some point They were sitting there and they were telling them, you have to add another 400 meters to this building when the foundations are already there. Now, this was achieved, again, with very, very innovative wind engineering, because effectively all they did is start changing the shape of the building in such a way that they could actually achieve for the foundations the appropriate loads in such a way that the building could be extended at much, much, much higher level. Okay? So effectively, all this stuff that is here are the bricks that enable at the end for this individual, to be able to design this building. This person has a name, okay? This person is a professional and is at the top of the pecking order. So when people talk about the structural engineer that designed the Burj Khalifa, you talk about Bill Baker, okay? And Bill Baker has the gold medal of the Institution of Structural Engineers. Bill Baker is a member of the National Academy of Engineering in the United States, and he is one of the world's leading structural engineers. Okay? And he represents a body of knowledge that has been built all the way from rank. Okay? That's what knowledge continuity is. And that is what enables professional competency to the highest level so that you can design something like the Burj Khalifa. You don't wake up in the morning and create out of pure imagination the design of the Burj Khalifa. That, does not happen. Okay? It might happen in software engineering, but it does not happen in structural engineering. Is that okay? So the question is this the same when you're dealing with fire? And I think we need to really think about the problem, and we need to really think about the challenges and the knowledge base that we have. Now, our problems are not less complicated. Our problems are equal or more complicated than the Burj Khalifa. This is our problem. How do you guarantee the fire safety of the International Space Station? This is not a problem that is easier to solve than designing the tallest building in the world. This is a very unique space, a very unique concept, where effectively you have to come up with an incredible set of innovations that are based in an enormous amount of knowledge. Now, but the question is, where does that knowledge come from? And how old is that knowledge? And how effective have we been at transferring that knowledge? And what we realize is that actually it started in exactly the same place. So this gentleman here actually was one of those people that was a Renaissance man, because also he developed all the thermodynamic cycles that are the basis of combustion theory. And it all started with William Rankine. So effectively the Rankine cycle is the same Rankine that the Rankine of statics. So it is exactly the same person that effectively started developing all this. And then it started bifurcating, but it started bifurcating in a very interesting way, because as opposed to hardcore structural engineering, we enter another very interesting space, which is the space of devices to try to protect for fire. And as you can see, the first sprinklers were developed in 1812. So we were already devising fire protection systems 200 years ago. Okay? And this guy, William Congreve, developed the first set of sprinklers, that was originally applied for industrial premises, to try to basically come up with a firefighter that was automatic. The whole idea was that we recognized that for certain types of facilities, the fire grew too fast and the firefighters could not arrive on time. So we wanted firefighting to happen immediately after the fire started. So these systems, effectively what they had was fusible links, and those fusible links will melt, the thing will move, and it will open a valve, and water will come out. Okay? This was a very primitive version of that device, but it's not that different to what we have today. But as you can see, it's about 200 years old. So a lot of this technology entered the construction industry through this gentleman called James Braidwood, and at the time, there was a very interesting relationship between building and firefighting. Many firefighters were actually people that were very well versed in building. They understood building. So James Braidwood started his professional life as a builder. His father was a builder, he was a builder, and they built many complex buildings. And then eventually he became a firefighter. He became the chief fire master of Edinburgh and then moved to London and became the head of the fire brigades in London, and he died in one of the London Great Fires. This book, Fire Prevention and Extinction, is effectively a formalized version of all the knowledge that we had in the mid-1800s of construction materials. So he's talking about non-combustible materials on the design of facade systems in such a way that they don't propagate fires, on roofs so that they don't propagate fires, separation distances between buildings. All that information is in there, but it's all presented in terms of how does that enable the fighting of fires. So the link between the fire service and the technology of construction is very, very solid at the time. And it becomes almost a marriage between the two. People could not conceive the idea of construction or firefighting as two independent things. Now, this creates a great advantage at the time, but a problem much later, because the association between firefighting and fire safety engineering becomes one such that they cannot be separated. So there is no separation of the two professions. It's considered to be a single profession that effectively delivers both. So if you build the building properly, that basically means you can fight a fire effectively. Okay? So the whole idea is that the two things are one, and only by building properly you can fight fires correctly. So you can only enable the performance of the firefighter if the building is designed correctly. Okay? So at this point, the two disciplines were the same. Now, if you look at the previous diagram, when I was talking about the design of the tall buildings, the same thing happens between civil engineering and architecture. At some point, civil engineering and architecture were perceived more or less as being the same thing. And architects were almost civil engineers, and civil engineers were almost architects. It was basically the same thing. Now, interestingly enough, by the time we get to the 1930s, when I was talking about the Chrysler Building, by then there's already a very clear differentiation of the two professions, and there is no marriage between the two of them anymore. Here, the firefighting profession and fire safety engineering are married around the idea that the two systems operate as one. Okay? And that marriage is one that is going to remain for a very long period of time. So then comes Michael Faraday, and Michael Faraday effectively is the first person who starts describing combustion systems. So our first understanding of how a diffusion flame works dates to the explanation of how a candle burns. So a very simple system where you have the first concept of a diffusion flame that defines the idea of a fire. So as you can see, the knowledge base is not new. You know, it's all 200-year-old knowledge that is accumulating little by little, and we're putting all the components in place. So we're putting the building technology, we're putting the fire protection, we're putting the understanding of the fire dynamics that is based on thermodynamics as defined by Rankine. So the whole thing is fitting together, creating a body of knowledge that enables us to understand not only the fire, but the consequences of the fire on infrastructure and actually how to fight a fire in an effective way. Okay? So then comes John Rigby Freeman, and this is a very interesting character. So John Rigby Freeman he's based in the United States, and he developed the whole analysis of hydraulics for fire protection systems. So he was the founder of Factory Mutual, which was a conglomerate of insurance companies that effectively created a whole framework to try to regulate the way in which we do fire protection. In other words, how do we implement protection systems that enables us to fight the fire in a fairly automatic way? Now, he's famous for another thing that is quite interesting, actually. You know, he was the first chair of the Department of Civil Engineering at the Massachusetts Institute of Technology. So that lesser activity was sort of his hobby, and but in reality, he was a fire safety engineer. So it is really interesting when you go to MIT, there's a massive portrait of John Ripley Freeman in the Department of Civil Engineering, and the label that says, first head of civil engineering at MIT, and the man is holding a sprinkler in his hand, which is pretty interesting actually. But he became famous more for creating FM Global, what is today FM Global, Factory Mutual, than for being the head or founding head of the Department of Civil Engineering at MIT. So what can you see here? You can see a long history, you can see great reputation, you can see a lot of skills, a complex problem, everything is being built up, okay? And it keeps going on. So then comes Ingber in the 1920s, again linking all this knowledge back into the idea of buildings. So what Ingber did was basically he turned combustion into a temperature versus time curve by basically standardizing the concept of a fire load. So he created the load that a fire imposes on a structure and created this brilliant concept of the standard temperature time curve that prevails until today, but this is 1928. Now this is a true engineering achievement, because effectively he summarized an incredibly complex process like a diffusion flame into a very simple temperature versus time concept that served as an engineering tool that enabled us to introduce fire as a load into structural design. So as you can see, everything is coming together. And like that, then the sequence keeps going. So then we start understanding better how that fire becomes a load, and that's the compartment fire framework, and that's Philip Thomas, and Kunio Kawagoe, and I can keep going, Tibor Harmathy, and you can keep putting on and on Howard Emmons, and all these people keep coming in until eventually you get to education and the formalization of the discipline in the early 1970s at the University of Edinburgh, when effectively David Raspash and Dougal Drysdale actually developed the first scientifically based fire engineering program in 1972. Okay, so we are now delivering engineers. Now let me ask you the question. Are we a new engineering discipline? Not at all. We're as mature, as well structured, as established, with as complex of a body of knowledge as any other discipline. So why do we claim that we are children? So why do we always use that excuse that fire safety is not a mature discipline? I mean, that's a very, very complicated question to answer because there is no reason for it. We should never be claiming that. We have a history as long and as prominent as any other engineering discipline. And we've done fundamentally everything the same way everybody else has done it. The question is, sorry, I forgot Jim Quintieri. Should never forget Jim Quintieri. So anyway, what he did was he developed tools, for the engineer, like test methods and all these things on the basis of engineering principles. So anyway, the question is, who are we? Okay? Are we really an engineering discipline? And why are we so different to everybody else? And why do we find ourselves in the pickle in which we find ourselves today? So we have even demonstrated, that we can actually design and build some of the most innovative structures in the world. So, anybody who knows anything about fire engineering will know about the Georges Pompidou and about Margaret Law as one of the preeminent fire engineers who actually deliver some of the most innovative structures you could possibly imagine. So we've even exercised the profession at the highest possible technical level. So what Margaret Law did was not hand-waving. There were thorough, rigorous, detailed calculations that enabled the design of a very, very unique building. Okay, and like this, the HSBC Bank in Hong Kong, Stansted Airport, you can name it. There's dozens of buildings that were built by Margaret Law in the 1980s using the most sophisticated tools. And nobody will question the competency of Margaret Law. She was the Bill Baker of structural engineering. The one person that if she walked into a room, everybody will agree with her because it was Margaret Law. Okay, you will put her name in there just to show that you were putting the most sophisticated fire engineering into your building. Now, what happened? Why did we lose all that if we had actually, by the early 1980s, achieved that level of prominence? You know, keep in mind who the architects of this type of buildings were. I mean, she was working with Richard Rogers and Renzo Piano in this building. You know, she worked with Norman Foster in the HSBC. She worked with all the star architects, and they would go calling for Margaret Law, the same way they call for Bill Baker when they want the structural engineering design to be done. You know, you mentioned that, Julie. You said, well, they should be calling somebody. Well, they used to call Margaret Law. Okay, we don't do that anymore. We've lost all that. That's because we're a young discipline? Not really. Okay, we have to think better. Where we messed up was that we allowed the pipe to dry out. And that broke the continuity of knowledge. If you really think about it, after Margaret Law, there was nobody else. There is no second Margaret Law. You know, I can continue to trace the structural engineers, you know, Fazlul Khan, you know, Billington, you name it. You can go one after the other one, and the knowledge continuity continued until today. But we allowed the pipe to dry out. Okay, some of you were at the combustion school in Chile, and you could see that there was a very interesting generational gap. So there was the people who talked in the first day, who effectively are all in their 80s and 90s. Okay? And then there's the people that came at the end of the week, which were in their 40s. And in between, there is nothing. Why did that happen? So why, while in other professions, everything continued and the pipeline remained filled and the knowledge continued to build, why in our field we have a gap of 40 years where there is nothing? Why did the pipe dry out? That's the real question that we should be asking ourselves. Where did we mess up that we allowed the pipe to dry out? Okay, and the answer is actually a very, very interesting one, because it is not a simple answer. Because if you look at technology, you will realize that in the meantime, in those 40 years, a lot happened. And everybody was innovating like crazy. If you look at the tallest buildings in the world, none of these buildings existed 40 years ago. 39 out of the top 40 tallest buildings in the world have been built after the year 2000. If you look at the airports, this is Istanbul in 1972. So this is Istanbul today. This airport now is the biggest airport in the world. And you walk in there and it's an absolutely enormous building of a level of complexity. You know, Grimshaw, the architect, designed that building, and you look at that building and you wonder, what on earth is going on that you have these enormous buildings? When we were doing housing in the 1970s, this is a concrete building in the outskirts of London, and we were so obsessed with means of egress that look how we separated the stair. We didn't even put it in the building. Look what we do today. Same height. This is a timber building with a single staircase. So that's what we do now for low-income housing. So as you can see, while our pipe was completely dry for 40 years, the rest of the world was going like crazy. And they continued to innovate and change and change and change. So we were sitting there doing nothing while everybody else was moving at a speed that was extraordinary. That's where we are in a pickle. Because the problem that we have right now is so much bigger than what we can handle, that we don't really know what to do, and we are static, standing in there waiting for somebody to fix the problem for us. Okay, but I go back to the question of what happened. You know, because obviously the brightness and the light disappears, you know, and the darkness comes in and the fog, and we're all in desperate reflection of what are we going to do with our lives. But the reality is that we really need to understand what happens if we're going to fix it, because the problem is actually very serious. Now, this is the answer to the question, and it's a very, very interesting one. So if you look at Telford, so this is the first professional institution that was developed in the United Kingdom. Now, why am I taking the United Kingdom? Because the United Kingdom was a precursor in all this space. So a lot of these structures then were exported around the world, and you will see the same things appearing in America, in France, in other places. Clearly, to the colonies, things got a little bit later, and they were generally copies of what the British did, so let me just stick to what the British did. So, 1818, the Institution of Civil Engineers was formed, and look how it's defined. It is defined as an independent, professional association for civil engineers and a charitable body in the United Kingdom. Okay? So, professional association that is independent, and it is for and by civil engineers. Okay? So they finally decided that they needed to professionalize their discipline because they recognized that the problem was of sufficient importance and complexity that only professional civil engineers could handle it. Okay? So just like that, it kept happening. And the architects decided that if they do it, then we should do it ourselves. And they recognized that being an architect is not the same as being an engineer. And they decided to part from the civil engineers, and 20 years later, they formed the Royal Institute of British Architects. Okay? So if you want to have a dull building designed by an engineer, okay, then you just have to walk outside this building and look at Dillon's house. It's a box. Okay, so the architects believed that that was not appropriate.
When was it built?
So the architects decided that that was not appropriate, and that they had to form their own organization, which effectively represented, again, a complex discipline that has societal interest and was of sufficient importance to merit a professional body for architects and by architects, again, in the United Kingdom. Is that okay? As we keep progressing and technology keeps evolving, the divorces keep happening because people recognize that then there is an aspect of civil engineering that requires specialist knowledge. And all of a sudden, you create the Institution of Structural Engineers, which is again a professional body for structural engineering based in the United Kingdom. Okay? And it keeps going on and on and on. And as systems become more complex, there is more and more of these organizations. So for example, all the way up to 1976, you get the Chartered Institution of Building Services Engineering. That's the beginning of the introduction of complex air management systems in buildings and so forth. So it required a professional engineering association that effectively represented building services engineers for and by building services engineering to differentiate them from everybody else. So they're no longer mechanical engineers, electrical engineers, architectural engineers, none of this. Now they are building services engineers. Okay? So, where do the fire engineers sit in there? How old are we? Well, we're actually older than the majority of them. Okay? So we started actually quite early. Okay? And here we are in 1918. So the Institution of Fire Engineers got formed in 1918, but it's a very particular organization because the Institution of Fire Engineers is a worldwide body that provides research, training, conferences, and professional qualifications for firefighters and civilians who work in the fields relating to firefighting, the science of firefighting and prevention, and related technologies. I rest my case, no? Why did the pipeline dry? We never claimed the space. The divorce never happened. From Braidwood in the 1830s and 1840s, where the two disciplines were one, as complexity started building up, and we built up all this knowledge, and there's the Ingbergs and the Quintieris and the Thomases and the Dreisels, and we put education, we create tools, we do everything that everybody else does. But what did we forget to do? Claim our professional space. So what's the result? Anybody can do our job. We have no professional monopoly. So if everybody can do our job, what is the value of being a fire engineer? 0. And if the value is 0, who's going to get into that profession?
Nobody.
Nobody. So,
all of these people.
well, you see, I have the privilege of being old and rickety, so I'm retiring. Okay, this is not my problem anymore. Okay, it is your problem. So claiming the profession is your problem. Okay, you have a great advantage because keep in mind that there was nothing. But now, there is UQ, there's academics working here, there's students being educated, graduating, entering the discipline. Okay, the same thing is happening in the United Kingdom, the same thing happened with the international masters in Europe, in Lund, in the United States. There's a whole new generation. Okay, and that generation is as big as it has ever been. Okay, and this is the moment where you need to claim your space. And the moment where you claim your space, then is when you start differentiating yourselves. Now, this is an ideal moment because everybody else is wondering what to do. You have the ministers running around trying to understand how to fix this problem. You have everybody wondering, how are we going to solve this problem? Okay? And the reality is that there is only one solution to it. And that solution is written in yellow. Okay? A professional association. Okay? The recognition that fire engineering is a discipline that is distinctly different from firefighting. That doesn't mean that a firefighter cannot be a fire engineer, or doesn't mean that a fire engineer cannot be a firefighter. Okay? All that it means is that the two disciplines are distinctly different. Now, I don't know if any of you has read the Phase 1 report of Martin Moore-Beck in regards of Grenfell Tower. Who was the #1 culprit that was highlighted by the judge in the Phase 1 report? It was the incompetence of the firefighters. Okay? Now, why the firefighters were deemed to be incompetent? Because they faced a problem that required them to be engineers. Okay, they were not behaving as firefighters anymore. They had to make engineering decisions that enabled them to understand how the whole fire safety strategy was crumbling to pieces, and they couldn't remain following the behavior of firefighting, which is effectively following a prescribed protocol. They had a prescribed protocol of defending place with a stay-put strategy by which everybody should remain in place, and the primary objective was to fight the fire. They should have thought as engineers and change the strategy into a strategy of evacuating everybody, okay, and put down the idea of fighting the fire. They should have not fought the fire, they should have got in and evacuated people. And they didn't do it because it's a distinctly different profession. Firefighters cannot think like fire engineers. They don't have the skills, they don't have the knowledge, they have a very different set of skills. So here we are stuck in a marriage that is effectively killing both parts of the couple. Okay? Because the firefighters are not going to come out clean from this one. Okay? Nor the fire engineers. And the problem is not going to go away. So in many ways, there has never ever been an opportunity like the one we have today to claim the space. And if you decide as professionals to ignore it, you are effectively dooming your career to be subordinate to individuals that don't understand what needs to be understood. Okay, so this is the moment to actually change our roles and start putting the yellow into our own professional organization. And again, I repeat the same thing, that is not my problem anymore. That is your responsibility. Okay? So you have to think very, very careful about that, because effectively that is what is at the source of the problem. Okay? Keep in mind that knowledge has to build up, and these complex problems require that knowledge build up. For that, you need to have a filled pipeline of professionals, and the only way to have a filled pipeline of professionals is adding value to the profession. And if you don't define the profession will never have value, and therefore the pipeline will continue to be dry. Okay? So we have to be very careful to take the opportunity and actually do what needs to be done. So, right now, what we have is an enormous confusion of competency, because we have not been able to fully sign off the divorce papers with the fire service. Okay? We're still married, and we have two professions that conflict because of the complexity of the problem, and therefore the confusion of competency is the one that is creating all the problems that we have. So, to finalize, how can this be fixed? Very straightforward. You have to recognize the professional nature of the discipline as a distinct professional discipline from firefighting. It is not the same profession. Okay? We have to define and formally recognize competencies and attributes associated to professional practice. So we really need to define the discipline correctly so that it covers all the subject areas that effectively are part of that discipline. You know, we need to clearly define and enforce the boundaries of the profession, and we need to invest in high quality professional education, accreditation, and representation. And it's up to you to push for all of that, because that's what's going to define, you know, your professional life. So at the end, you want to implement as many interim measures as necessary while the talent pipeline fills in, but you know, this is a moment to get started. If we wait for another 10 years, the problem is just going to be bigger. You know, and it's going to be more complex, and it's going to be more difficult to change, and it's very unlikely that the convergence of factors is going to come up into this position again. We have never been in a position where we are in a crisis and we have means to respond. We have educational models, we have graduates, we have competent people in the field, so we have ways to demonstrate why we are valuable. And the truth of the matter is that that has never happened before. So here we are in a position where we can make a difference, and I hope that you take that very seriously, because at the end, as I said before, it is your responsibility. So, is this easy? Clearly not. Okay, it is going to be really tough, because obviously that implies displacing a lot of people. It implies questioning the competence of many, you know, and it implies coming up to a position where firefighters and fire engineers learn to respect each other, because not of their common enemy, but because of their own unique differences, because that's what makes them valuable. So it is not about saying that the firefighters are incompetent or that the engineers don't know what they're doing. It is effectively about saying, this is your space and this is mine. Okay? So who has to do this? You. Okay? Do you have a choice? Unfortunately, no. Okay? So effectively, this is a time, and you really do not have a choice. Thank you. Happy to answer any questions. Yes.
So, Professor, thank you. I mean, I 100% agree with you in terms of the space that the necessity for the professional organization, but you also pointed out the divorce of the structural engineering and the architecture. So, but due to many factors, or probably we could also say that the way the institutions, the education institutions that deliver the structural engineering, it is a field which is going in a trajectory to become redundant, and where you are seeing the remarriage of the architecture and structural engineering together to the master builder concept. So in that space, then how does the dynamics of the fire engineering is going to work?
Well, I mean, I think that you know, I think I will argue against the fact that structural engineering is redundant. I think structural engineering is evolving, you know, and most of the traditional jobs of structural engineering can be automatized to a point. that effectively you can transfer them down to another discipline. That is just a change in the boundaries. Okay? But if you want to do a very unique piece of structure, or you want to do something that is different and outside of the norm, you are not going to rely on an architect to do that for you. You still require a structural engineer with a certain set of skills. I think if you look at the evolution of all these disciplines, they're constantly changing, and the evolution is always going to be there, and the boundaries are always going to shift. And there are disciplines that have been submerged into other ones in the process, and other ones that have split. So we cannot consider this as a static process. Okay? And yes, in the next decades, structural engineering is going to see a very significant shift, you know, into something that is very different to what probably structural engineering was 20 years ago. And that's perfectly fine, because the pipeline is full. So structural engineers are constantly revisiting their boundaries, and they're redefining their profession in a way such that the relevance remains there. Okay, it remains in a different space, but it's still there. Okay, and the organizations themselves are active enough at defending their own interests that they maintain a certain space of relevance for themselves. So I don't agree with you that structural engineering is going to disappear. No, it's just going to morph, and it's going to continue to change as knowledge evolves. But then you will have a pipeline that enables the change to happen in a proper manner, which is what it really is happening. You know, it's not happening in fire engineering. You know? So if you look at the institution of fire engineers, it's about 10,000 members, of which only about 300 are engineers. The other 9,700 are firefighters. So we are guests in their space, and we have never been able to create or carve our space, so that's why we don't have a pipeline. You're silenced by the weight of responsibility? Yeah.
I mean,